Hi, well, I'm Stephen Neshiba, and I'm here to help you out a little bit with one of the additional homework problems. And the homework problem is a derivation, and it just says something like this. Given that pi sub t is equal to a over b squared for van der Waals gas, then that implies that mu sub t, the isothermal Joule-Thomson coefficient, is approximately equal to that expression where a and little b are the van der Waals parameters. And I'm using volume as the molar volume just to keep the notation simple, so we have n equals 1. So how do we go about that? Well, here's a way to start. We're going to start off with the definition of the enthalpy, and the enthalpy is equal to U plus PV. And what we're trying to do is get an expression with the left-hand side is mu sub t. So that's the derivative of the enthalpy with respect to the pressure. So I need to put it in differential form. So I've done that here. Here's the product rule applied to this definition. dH must be du plus product rule applied to the PV term. And so that's just calculus. And now the second step here, what I've done is I've said, okay, this is the differential equation of state for the internal energy, and that's of course where CV and pi sub t come in. That's fine, and that's good because we have that's the piece of information that we need to use for this derivation. And this is just the PdV and ddP part coming in here. Now the next step is the direct partial. It says HPT is equal to the derivative with respect to pressure, constant temperature, all the rest of that stuff on the right. And as usual, the constants stay out, so that's CV, TPT. Here I've collected both of the terms. That's a dV and a dV, so it's, I've collected the pi sub t and the pressure term, and all multiplied by VPT. And then we have that last term, and we have a couple of things that we can do here. The derivative of temperature with respect to pressure, when we keep the temperature constant, is of course 0, and then PPT is that term right there is 1. So we have that term times VPT plus the volume. And how are we going to deal with this? Well, it's a little bit awkward because you can't solve van der Waals equation. Here's the van der Waals equation of state. You can't solve that explicitly for the volume. So you get a cubic equation if you try to do that, and it's kind of awkward. But what you can do is you can just take the derivative of the pressure with respect to volume, holding the temperature constant, just by taking that derivative right there. And then by the inverter, we know that that is 1 over VPT. Okay? So you can get that. This thing is 1 over that, and that's a good foothold into this problem. Okay.